The Webb telescope glances so far out that it is catching light that has already been voyaging for over 13 billion years. Yet, the universe has been expanding, and thus the light has been stretching as well. The majority of distant worlds we observe in time date back nearly to the Big Bang. The immensity of the universe might seem vast, but every last bit of it started from what we allude to as the singularity. As of now, this is how we apply the Big Bang Theory's interpretation. Anyway, the James Webb Space Telescope, JWST, has shed light on important mysteries concerning the formation and growth of the universe, leaving us dumbfounded. Prestigious physicist Brian Cox has proclaimed that the noteworthy discoveries made by the JWST might actually reshape our understanding of the universe as a whole. Join us as we delve into these brand new discoveries about the heavens that promise to alter our understanding. The Space Telescope, named after the recognized NASA executive James E. Webb, remains a wonder in current galactic investigation. This telescope represents a huge mechanical leap forward from its predecessor, the Hubble Space Telescope. Resulting from a cooperative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST surpasses the abilities of its predecessor. It utilizes cutting-edge technology and a design enhanced for concentrating on the universe in incredibly fine detail. Unlike the Hubble, the JWST conveys clear and sharp images of faraway heavenly bodies, primarily operating in the fascinating infrared range. This component enables it to penetrate astronomical dust and capture divine objects that were previously hidden from our view. With its massive 6.5-meter primary mirror made up of 18 hexagonal sections, the JWST dwarfs the Hubble's reflector. Situated roughly 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in harmony with Earth, ensuring a constant and steady view of the universe. While looking into the far-off corners of the universe, it involves exploring light years, but also a type of time travel. The JWST uses infrared instruments to observe heavenly objects and events going back billions of years. The light from these things, as a result of the expanding universe, moves through a red shift from the visible spectrum to the infrared frequency. Luckily, the JWST can identify infrared light emitted by heavenly bodies that are far away, enabling researchers to investigate the birth of stars, explore galaxy development, and examine exoplanet atmospheres. Its latest historic discovery involves identifying an incomprehensible mass of cosmic systems at the very edge of the observable universe. This finding casts doubt on the veracity of the current theory of how things came to be, causing us to re-evaluate key cosmological assumptions. To comprehend how we got to this point, we ought to go on a brief excursion through the history of space investigation. Early civilizations, such as the Greeks and Chinese, laid the foundation for understanding planetary movement by observing celestial bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. In the mid-20th century, Edwin Hubble, an influential astronomer, made historic discoveries in cosmology. His observational approach to space science uncovered that distant nebulae were isolated worlds beyond the Milky Way, changing our understanding of the universe's size and expansion. Thanks to Hubble's law, established by him, we now know that galaxies farther away are moving away at higher rates, demonstrating the universe's expansion. Space exploration during World War II marked the beginning of the space race. With the Soviet Union's Sputnik in 1957 as the first artificial satellite in orbit, Yuri Gagarin's orbital trip in 1961, and the Apollo 11 moon landing in 1969, humanity achieved crucial milestones. Fast forward to 1990, when the Hubble Space Telescope was launched, providing exceptional clarity and stunning insights into the universe. The journey from ancient observations to the technological wonders of the James Webb Space Telescope showcases the constant development of our understanding of the universe. Take the Hubble Space Telescope, HST, for instance. It captured the well-known Pillars of Creation image in the Eagle Nebula, displaying a star nursery composed of massive columns of gas and dust. Another significant accomplishment was the Hubble Deep Field, capturing thousands of galaxies in what seemed like an empty patch of space. The HST also dove into exoplanet atmospheres, pinpointing elements like water and organic molecules, referring to distant worlds and the possibility of habitable zones beyond our solar system. Following the development of the closest observed supernova, SN 1987A, it provided insight into the life cycle of massive stars. These achievements cemented the Hubble Space Telescope's legacy as a cornerstone of modern cosmology, dazzling the world with its incredible and significant discoveries. The James Webb Space Telescope was launched to advance technological achievements and apply the lessons learned from its predecessor. The prevailing theory of the universe's origins suggests that approximately 13.8 billion years ago, the universe began as a seriously hot and dense singularity. With rapid expansion, it gave rise to matter, energy, and the fundamental forces that govern the universe. As it expanded, it cooled, leading to the formation of atoms, stars, galaxies, and the various structures observed today. The Big Bang Theory also explains cosmic physics, including the cosmic microwave background radiation, element abundance, and the large-scale structure of the universe. Despite being widely accepted, the Big Bang Theory faced skepticism and challenges in its early days. Alternative models, like the steady-state theory, suggested a universe without a specific beginning. Concerns about evidence supporting the initial singularity, expansion, and observed anomalies arose. Over time, most objections were addressed. A significant piece of evidence came with the discovery of cosmic microwave background radiation in 1965, aligning with Big Bang predictions. Space missions like WMAP and COBE, along with technological advancements, further supported the theory. Accurate measurements of cosmic microwave background radiation matched theoretical predictions remarkably well. Enter the James Webb Space Telescope, equipped with advanced infrared instruments capable of peering through cosmic dust. Operating primarily in the infrared range, the JWST captures the oldest light in the universe and observes the formation of objects shortly after the Big Bang. Its infrared capabilities allow it to focus on the formation of stars, celestial nurseries, and regions invisible to the human eye. Infrared light, with longer wavelengths compared to visible light, can penetrate dust clouds around stars, overcoming a limitation of the Hubble Space Telescope. The JWST can observe cooler objects that emit mainly infrared light, making it ideal for researching phenomena like exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their emitted light waves get stretched, causing a shift toward longer wavelengths, known as redshift. The JWST's infrared capabilities enable it to detect these redshifted signals, capturing light from the early universe and offering insights into its formation and evolution. Intense events like black hole mergers or the birth of new stars primarily occur in. Furthermore, the JWST's capabilities allow scientists to study the atmospheres of exoplanets, offering insights into their potential habitability. By analyzing the chemical composition of distant planets, astronomers can detect signs of water vapor, carbon dioxide, methane, and other molecules essential for life as we know it. This advancement brings us closer to answering one of humanity's greatest questions: are we alone in the universe? One of the most groundbreaking findings involves observing exoplanets within the habitable zones of their stars. These regions, where conditions might allow liquid water to exist, are crucial in the search for extraterrestrial life. The JWST's ability to measure the light passing through an exoplanet's atmosphere helps scientists infer the presence of key elements and compounds. Recently, it identified carbon dioxide in the atmosphere of an exoplanet known as WASP-39b, a milestone in exoplanet research that demonstrates the telescope's extraordinary sensitivity. Additionally, the JWST has provided unprecedented views of star formation within dense molecular clouds, regions that were previously opaque to optical telescopes like Hubble. By peering through layers of cosmic dust, the telescope has captured the early stages of stellar birth, revealing how protostars gather mass from their surroundings. This insight deepens our understanding of how stars like our Sun formed billions of years ago, shedding light on the processes that shaped our solar system. Another significant discovery involves black holes, particularly the supermassive black holes that reside at the centers of galaxies. The JWST has detected light from material spiraling into these black holes, providing clues about their growth and influence on galaxy evolution. Its infrared instruments can observe the interactions between black holes and their host galaxies, revealing how these massive objects affect star formation and galactic dynamics. One of the most astonishing revelations is the detection of galaxies that challenge existing cosmological models. Some of these galaxies appear more massive and mature than expected for their age, raising questions about how quickly galaxies formed after the Big Bang. This unexpected finding has led scientists to reconsider the timeline of galaxy formation, suggesting that the early universe may have been more dynamic and complex than previously thought. Moreover, the telescope's deep-field images have unveiled galaxies that existed less than 300 million years after the Big Bang. These ancient galaxies, which are among the earliest structures in the universe, offer a glimpse into the cosmic dawn, a period when the first stars and galaxies began to illuminate the cosmos. Studying these primordial galaxies helps scientists understand how the universe transitioned from a dark, featureless expanse into the vibrant, structured cosmos we see today. In addition to its contributions to astrophysics and cosmology, the JWST has also advanced our understanding of planetary science within our solar system. It has captured detailed images of planets like Jupiter, revealing intricate details of its atmosphere, including the planet's powerful storms and auroras. The telescope's infrared capabilities allow scientists to study the composition and thermal properties of celestial bodies, offering new insights into the formation and evolution of planets, moons, and asteroids. Looking ahead, the JWST's future observations promise to unlock even more cosmic secrets. Scientists plan to use the telescope to study the atmospheres of Earth-sized exoplanets in the habitable zones of stars like TRAPPIST-1. These observations could reveal signs of life or conditions conducive to life, bringing us closer to answering profound questions about our place in the universe. As technology continues to advance, the James Webb Space Telescope stands as a testament to human ingenuity and curiosity. Its discoveries are reshaping our understanding of the universe, from the earliest moments after the Big Bang to the formation of galaxies, stars, and planets. With each new observation, the JWST is expanding the boundaries of human knowledge, inspiring future generations of scientists, astronomers, and explorers. In conclusion, the James Webb Space Telescope is not just a scientific instrument. It is a time machine that allows us to explore the origins of the universe and our place within it. Its discoveries are challenging existing theories, revealing hidden wonders, and opening new avenues of exploration. As we continue to unravel the mysteries of the cosmos, the JWST will undoubtedly play a central role in shaping the future of astronomy and deepening our understanding of the universe. Regarding the fundamental character of the universe, including its composition, structure, and the factors that control its evolution. While the Hubble Space Telescope was revolutionary, it was limited in its ability to observe the early universe. Its main limitation was its inability to effectively penetrate cosmic dust and detect the infrared light emitted by ancient galaxies. Older telescopes relied on visible and ultraviolet light observations, making it challenging to explore the early universe, where these wavelengths are absorbed or distorted by interstellar gas and dust. The James Webb Space Telescope, JWST, represents a significant leap forward in observing galaxies from the universe's initial stages. In contrast to its predecessors, the JWST can observe celestial objects that formed within a few 100 million years after the Big Bang. Using its infrared sensitivity and modern imaging techniques, the JWST has uncovered an abundance of ancient galaxies, offering remarkable clarity and detail in understanding the universe's evolutionary history. Preliminary results from the JWST's observations have sparked waves in established cosmological models. The detailed data challenges several aspects of prevailing theories, prompting cosmologists to reconsider fundamental principles governing cosmic evolution and structure. Discrepancies between observed data and theoretical predictions have sparked intense debates within the scientific community. Observations have revealed a larger number of galaxies at the beginning of the universe than anticipated by existing models, suggesting a more complex and rapid evolution process. Some observed early galaxies appear more developed than expected, challenging conventional models that forecast slower development. The discovery of an unfathomable mass of galaxies challenges the assumed distribution and arrangement of large structures, revealing a more intricate and denser cosmic web than previously thought. These observations raise fascinating questions and avenues for further exploration. The existence of large structures challenges early models of cosmic structure formation, resulting in researchers refining models to explain how vast structures gathered rapidly after the Big Bang. This presents a puzzle that requires justification without violating fundamental cosmological concepts. Significant disparities in the universe's early conditions compared to predictions based on existing models have also been revealed. These variations may suggest previously unknown physical processes, unexpected conditions, or unidentified cosmic phenomena. In simple terms, these variations have prompted scientists to rethink and improve our models of the universe. All we can do at the moment is acknowledge that further exploration is required to incorporate these surprising observations into a more comprehensive understanding of the universe. Initial observations often provide exciting deep dives into the universe, but further investigations sometimes reveal differences. For example, early observations may show specific properties or arrangements within distant galaxies that, upon closer investigation, reveal alterations in their structure or evolutionary pathways. In conclusion, enormous phenomena are extremely intricate and require careful investigation for us to accurately understand their true nature. Spectroscopy, a method that helps unravel the characteristics and background of celestial objects, is an example of such an investigative tool. It involves analyzing the light emitted or absorbed by astronomical objects. By examining the properties of this light, spectroscopy provides detailed information about the temperature, density, chemical composition, and movement of celestial bodies. This analysis helps us understand the origins, development, and contributions of celestial bodies to the cosmic tapestry. The JWST has uncovered numerous cases where initial observations were later refined through additional investigation. For instance, initial observations of distant galaxies primarily suggested a straightforward structure dominated by lighter components, such as hydrogen and helium, in line with theoretical expectations. However, spectroscopic examination with the JWST revealed fascinating differences in elemental signatures, identifying heavier elements or compounds previously undetected or misunderstood in the early universe. This defies conventional ideas about the early universe's chemical composition and the mechanisms responsible for the development and dispersion of elements across vast distances. Similarly, initial assumptions about galaxies in the early universe were based on preliminary observations, suggesting a relatively uniform pattern of development and organization. However, more detailed investigations by the JWST revealed a much more diverse and complex array of chemical compositions within these galaxies. The James Webb Space Telescope, JWST, is constantly redefining our understanding of the cosmos by shedding light on previously unseen facets of the universe. One of its most exciting capabilities is its ability to study exoplanets in unprecedented detail. By studying the atmospheres of planets orbiting distant stars, the JWST can identify important chemical signatures, such as the presence of water vapor, carbon dioxide, methane, and other organic compounds. These findings provide valuable insights into the potential existence of habitable exoplanets and the conditions that could support life beyond Earth. In addition to exploring distant worlds, the JWST is changing our perception of star formation. It can observe the birth of stars in regions where young stars are surrounded by dense clouds of gas and dust that optical telescopes cannot penetrate. With its advanced infrared detection capabilities, the JWST records the faintest glimmers of these new stars as they emerge from the darkness, offering a clearer picture of the processes that lead to the formation of stars and planetary systems. By studying these regions, astronomers are gaining a deeper understanding of how stars like our Sun emerge from nothingness and change over time. Another remarkable aspect of the JWST's research is its ability to look inside the hearts of galaxies. Black holes, particularly supermassive ones, are thought to reside at the center of most large galaxies. The JWST's advanced instruments allow scientists to observe the behavior of matter around these black holes, providing new insights into their growth, their influence on galactic evolution, and the powerful jets of energy they produce. These findings help astronomers piece together the story of how galaxies and their central black holes evolve together, influencing each other's development. In addition, the JWST's discoveries are not only answering long-standing questions, but also raising new ones. As it probes deeper into the history of the universe, it is uncovering phenomena that challenge existing theories and models. These challenges drive the scientific community to refine current cosmological models and open up new avenues for research that were previously unimaginable. The discoveries of the JWST are not merely pushing the boundaries of our understanding. They're helping to reshape the fundamental principles of how we view the universe itself.